The lab that you did last week, I put down it was due, I think, yesterday or today at 0000 hours. I moved that to the 7th to 23:55. I think that's a clearer time because I got some messages last night. Is it due was it due this morning at midnight, or was it due at midnight tonight? And I just said, all right, we'll just make it that there. So you've got some time to turn it in. As I recall, I did not shut off the automatic lockout on that. I've done that before to where you can't turn it in late. That there, I did not shut that off. So even if you did turn it in after midnight, it would have taken it. So that there. So, but I went ahead and extended the due date until, I don't know when the 7th is. Today's what? Today is the 5th, so I guess that's Thursday or Wednesday that it's due then. So, and again, I'm not looking for large reports, just some kind of proof that you've actually played with the robots and you have an idea how they work. So today I'm going to just kind of introduce a couple of topics, and as I said, I normally would have sat down and did all my research yesterday and had my lab, my lecture all planned where I looked like I stole enough parts and I'm prepared. Unfortunately, yesterday I did not even turn on my computer, so I'm just going to go through pieces of what I have already installed at there. What I'm going to talk about today a little bit is the robots that we used. Has in it, and I'm not going to open up one of the robots to show you, it's got in it a little Arduino processor board. That's there. And so I'm going to talk a little bit and introduce the Arduino processor. That there. This is not a course on the Arduino, and if I had enough Arduino and enough servos, I would actually have you do a lab out there. I plan on demonstrating a lab for it, but as I said, I didn't prepare for it, over the weekend, and that was my plan, was to have that all ready to go. I've done it before, and it shouldn't take me that long. Probably could find the old files out there. It's not a case that it's something I haven't done. I've done it many times, but I don't have it there. But let me first off kind of talk a little bit about the Arduino. And this is the wrong set of slides. Let me go back to here. And well, I can go through that and use this tutorial to talk about that there, but there's no internet connection. Why am I? Connect. Okay. We will try this again. Okay. All right, let me just kind of go through, and I'll just use this picture as my guide right there. All right, this is the Arduino. I'll go ahead and pass it around so you can at least look at it. And so just kind of look at it because have a peek at it. What the Arduino is this is the Arduino Uno. It's been around about 12, 15 years. It's not a new project. It's been around for quite a while. It's a very popular board, especially with the BMI folks that have to do projects where they basically have to just build something. And building something with the Arduino is very easy because it's an extremely easy board to program. That there. And a lot of students really like them because you don't have to think like an engineer, you can think like a hobbyist with them. That there. So I did a pick on it because the Arduino was originally designed, and I'll talk about this in a little bit more detail, really with the high school, middle school student in mind. It wasn't designed with the university engineering student in mind, and it sure wasn't designed with the industrial engineer for real projects in mind. It was designed for hobbyists, for people to play with right there. So, so when I pick on our robots and the fact that it uses an Arduino, that tells me that the robots are really not for prime time use, but more for just for learning applications right there. But as we look at the Arduino from this picture here, and I'm looking at from this being my left side right here, we've got, on the bottom, we've got 6 analog inputs. Now these are true analog inputs. The Arduino's got built into it an analog to digital converter, so it can read analog signals between 0 and 5 volts. We got above that a little bit of our power. We've got our VN, which is typically some voltage that would go to, from a source. We've got 2 grounds. We've got a 5-volt source and a 3.3 volt source. We also have a reset pin to reset the microcontroller. And then we have the IO reference for the analogs, where we have to, and normally that's tied to just 5 volts or 3.3 volts, depending what we want our reference to be. On the right side here, we have some digital inputs right here. Pins 8 through 13 are digital inputs, and pins 0 and 1 are RX and TX for serial communications, for a serial port. And then pins 2 through 7 are our PWM or digital outputs, depending on how we set those up. Now, PWM stands for pulse width modulation, right there. And pulse width modulation basically means that we vary the output of the, and there's probably some slides that cover it, but I'm just going to try using my pen here and here. Go to XXX. That's not what I meant. That was, as a programming class, that was not a dirty word. That was actually supposed to be a line number that there. So, but PWM basically means that we have a period here. I'm just going to call this T. Now, that there. And we vary, T is from the beginning of our pulse to the end of our pulse, and then we have right there. So we've got T on, that's how long we're on. We've got T off, that's how long the signal's off, and we got big T, which is our duty cycle. TD, I'll use TD right there. Now normally we don't worry so much about the time off, but the time on plus the time off is equal to the duty period right there. So now our frequency is equal to 1 over TD. That's our frequency in which this thing operates at right there. And we can vary our time on from 0% to 100%. If our duty cycle or our time on is at 0%, then our output is 0. It's going to be just stay low. If it's 100%, it's going to stay on all the time. If it's 50%, it's going to run at half speed or half brightness, right? So PWM is a way of getting an analog voltage typically out of a microprocessor normally. Normally, if I wanted to say, for example, have an LED right here, right there, and we'll put in our typical current limiting resistor. This comes from our micro C, and this goes to ground right there, right there. If I want this LED to be full brightness, I would send it 100% duty cycle. If I want it to be barely on, I might send it 5%. If I want it half on, I might send it 50%. But I can control the brightness of this LED by controlling the duty cycle coming from the microcontroller right there. So if I have a motor right here, and I'm going to show this going through a driver right there. You would probably right there, and we would use a PWM signal right here. We can control the speed of the motor by turning it on and off at with certain duty cycles. The higher the duty cycle, the faster the motor is. Now, this is for a standard DC motor. I do a project, I've done a project in some of my other classes I've taught in the past, where I have the students build a robotic car, and they have to control the speed of the car. And the way they control the speed of the car is they control the pulse width modulation going to the tire, going to the two wheels. And then at the same time, I would then also vary the speed of one wheel versus the other in order to turn the car. So if I only have one wheel turn and the other one doesn't, the car would turn. Very common way of controlling DC motors is with PWM, right there. So, but this is with the standard DC motor. Now, as it turns out, we're not using, I ought to mark through that right there, because people think that that's my first comment when I got there, but that means go to line 100 or 200 in code. Talking about in my computer programming class that one of the things that people have done in the recent years of computer programming is they've eliminated the go-to statement that there. And I was kind of explaining what the go-to statement was, but you don't find it used much. You don't find it all in C, although you can have it in C. Okay. So, as it turns out, the Arduino has got 6 pins that have pulse width modulation already built into them, right there. And we only have to define these as pulse width modulator right there. Now, we also have, and I don't really have slides for it, but I'll talk about it, that we have what's called a servo motor. Now, a servo motor is a DC motor, but it has built into it electronics that if I give it a PWM signal of a certain width, it will stop. It'll go to zero, it'll go to 45 or 45 degrees. Actually, that's a continuous. I've got that confused. There's 2 types of servos. There's the normal servo, which that's what this is in my hand, and I'll pass it around too. These are what's used in the robot. There's 6 of these right there. And that's what this lab here will talk about. I will do this lab as a demo after I practice it at home. I'm not going to sit here and try doing it with that, and look like a fool trying to do it without testing it, especially with my brain kind of half in a fog today, right there. But because we've got 6 servos drives already built into the Arduino, that's one of the reasons why the robots we've got has 6 servos. That is the maximum that the Arduino can drive, right there. So, this kind of gives the parts for the Arduino, this particular lab, and this particular lab actually has parts to do this lab, and if I had enough parts in the lab kit, I would have you do the lab, but it's not really that important. It does work, so and I will do it as a demo, but we have our servo motor. Now this one's a little different than mine. It's got 3 pins is actually exactly the same, except for mine's got a white, red, and black. This has got orange, red, and black. So the only difference is mine's got a white wire on it. That there. It's a different brand. This is the Parallax. It's a more expensive one, actually, right there. But this particular servo will go between 0 and 180 degrees, right there. And I am not going to go into it, nor is it part of this course, discussing how electronics works. But if we give it a pulse signal between a certain value, it will go to a certain degree level, right there, right there. So that's the parts that they're. The layout for it is relatively simple. And again, I'm just going to kind of bring this here. They take the red, and the red goes over to the red here. That's my 5-volt power going to the servo. And that would go to the 5-volt pin on the Arduino board. We have the black, which is going to the ground, and that goes to the black line. And then we have the yellow, which is the white on my particular pin right there. And that goes to any of my PWM outputs right there. So, and right there. And as you can see, the PWMs here are pins 11, 10, 9, 6, 5, and 3. And that should match the board I just passed around. Right there. So I happen to, on this one here they use pin 9 as my. If you were to look at the robot and take it apart, you'll find that all 6 of these PWMs are used right there. So that there, and each one of those robot joints has got a servo motor that looks very much like. And we'll start to see this. Motor, and you can turn it with your hand and you feel it. It's got 180 degrees. Do me a favor, don't turn it past the stop. Boom. Yeah. So I actually bought these servos. There's probably some in one of the BMI labs, but until recently, ICO and BMI were separated, so I couldn't use that there. So that's the basic connection between the servo and the Arduino. And remember, the Arduino is nothing more than a microcontroller board. If you took the microcontroller course, back when I taught it, I was using the 8051. I was switching to the Raspberry Pi, but I think it went back to the 8051. That's also a microcontroller. The 8051 microcontroller board that we use in our microcontroller course is an industrial strength microcontroller. It's been around for quite a while. Right there. The Arduino is as I said, right there. Right there. Let me go back to right there. They talk about if the Arduino misbehaves. In other words, we found that some of these robots they'll sit there and go bzz, 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 like that there. The fix for that, but the designer of the robots did not put these in, is to put a capacitor between the VCC and ground in order to that there. Normally, these capacitors need to be as close to the motor as possible for it to work. Right there. So on the breadboard, right there. So the code, I'm going to kind of briefly go through the code, and I'm not going to go in great big depth into the code, but the code is relatively straightforward right here. This simply sweeps this from one end to the other. So all this does is, and this is the code I'll actually put together and I'll run it in class. You'll notice that this is standard. This is actually shown up, and it's what they call Python code. It's not C. It looks a lot like C, actually. Is this a C file? Doesn't look like it's. It looks like C actually to me. It doesn't look like Python. The Arduino can take both, but I think this looks like C syntax right there. In fact, I'm sure it is. You'll notice that the very first line of code in there here is we include a file called serval.h. In the serval or the Arduino library that comes with their IDE, and when you buy the servo motor or processor, the one that I passed around, you actually download. And one of the reasons I'm not demonstrating this because I changed computers since the last time I did this, so I haven't downloaded and installed this. Hopefully in the next day or two I'm waking up to do it. But when you download the IDE for the Arduino, right there, it plugs into the Arduino processor through a typical USB port right there. And you can write your code using any PC, and it's connected to the servo, and then you download it to the Arduino when you compile it, and it runs in the Arduino, just like on the 8051 or any other microcontroller. And it just so happens that the Arduino has built into it this nice little library here called serval.h. That's built into the library of the Arduino, so you don't have to think about how to write the servo code. It's done for you. It's built into the library right there. So you simply include the Arduino library header file for the servo motors. We initialize our servo motor to be pin 9, right there, servo pin. And we tell it with the keyword servo, and here we're saying servo right there, which is basically, I'm thinking that should be servo pin. That looks like that there. Well, no, it just simply says that servo is a capitalized word, and it's a keyword, and we're declaring a variable called servo right here. And we're saying that it's a servo motor right there. So we initialize the angle to 0, and our setup is we do serval.attach. Now this happens to be a function call within the servo class, and you did not take C++, so you probably haven't done any class function calls, but servo is a class, and attach happens to be a function or a method within that class. So in other words, we're attaching pin 9 right here, which is our servo pin, is being set up as a servo motor attached to pin 9 on our Arduino right there. So since this is of a class, there's another function type right here called servo write right here. And servo write simply is going to write to the servo motor pin whatever PWM signal is required to get the angle which we request. So this is a relatively simple loop that goes between 0 and 180 degrees, and it's going to increment at 1 degree per pass. Right there. So the first time through the loop, it's going to do a servo.write 0, then servo.write 1, servo.write 2, and it's going to go all the way up to 180 degrees or 179 degrees right there. And in between each loop, we have a delay of 15 nanoseconds roughly, or 15 microseconds. I don't know what that delay is. Depends on that. And then we simply servo it back. And this is all we have to do to control the motor. And so as I said, when you're writing code in MATLAB, you're talking to the servo. You're talking to the to the Arduino processor in MATLAB, and there's code in the Arduino that I can't get to. I don't have a copy of it. But there, I asked for a copy, but I don't have a copy. That just simply takes your code, uses the speed parameter which you set up early. You know, the very first line of code there. That speed parameter is used for this delay right there. So when you set the speed between 0 and 100%, and I think you set with the number 92 or something like that, or 80, I can't remember what you set. While we did in the demo, right there, that actually is translated to a delay in the Arduino code, right there. So that there, and then you tell it what motor, and again, this servo.write angle right there goes back to the fact that our particular one right here is, we do it in our setup, we've got one servo pin that we're connecting to. We'd have servo 0 through servo 5 if we were to write the code for the robot. We would have to set up 6 different variables. And remember, servo is a variable name right there. The second servo, not the first one. One with the capital is actually in the library. So this would be servo space lowercase servo 0, then servo lowercase servo 1, servo. We would have to set up 5 of those to control 5 motors right there, or 6 motors. We would have to have servo pin 0 through 5 right there. And remember our right here, we're only using 1 pin in this example here. In the robot, we would use 6 pins right there. Right there. Oh, I had the code right there. So in this particular case, we're only doing here. So the code that's in the Arduino that's in the robot actually talks to the PC, and it's looking for several instructions. The first instruction is looking for, well, after you set up the serial port and establish communications between the PC and the robot, is it's looking for the speed. You know, that's set one time at the beginning of your code after you connect. That speed, as I mentioned, is used for all the delays that are later on. Then what it's looking for is a servo motor number between 0 and 5. There's 6 motors there. 6 is the base, and 5 is the gripper, and then you have all the other motors in between, and then it would then set the angle right there, and then it'd go into a loop waiting for the next instruction for the next servo motor. So what's in the robot actually emulates what this code is that I'm showing here. That's what's in the robot in the servo right there. So it's talking to your PC, and it's running code that looks a little bit like what you're seeing right here, right there. So, but that's how we talk to the servo right there. Now, the sweep right here. Excuse me, there was another, Brett laid out for the knob. This particular one actually has a knob that we can put into it. Notice that the knob, you can see it from here. This is just a potentiometer, that's all it is. And a potentiometer has got 5 volts here, or 3.3, ground here, and this is our center tap right there to our potentiometer right there, and that's an analog voltage between either 0 and 5 volts, or 0 and 3.3. I didn't look to see where it's connected on here, but we'll see right there. It looks like it's connected to 5 volts, so it's 0 to 5 volts right there. So all we're doing is we're reading that potentiometer right there, and when we look at the potentiometer right there, we have the pot pin, which is pot pin is pin 0. And going back and looking at right here, you can see that our pot is going over here to our analog pin right over here. 0, right there, that's the center of the center tap right there. So we go ahead and we do our servo attach right there. And what we're doing is we're getting the angle right here from the pot right there. And what the pot is simply going to give us is a binary number between 0 and 1023. Right there, it's an analog port that we're reading. So we're going to, when we read that input, the potential of the pot, if it's connected all the way down to the 0 side, it's going to give us a value of 0. If it's all the way to the 5 volts, it's going to give us 1024. There, you can figure out how many bits the resolution that is. We divide that by 6 to get a rough idea of what the angle is going to be, and we just simply write to that. So by turning the pot, we can turn the motor how we want to turn it right there. So it's a relatively easy way of seeing how to control the servo motor right there. So this is the easiest way to do a robot arm right there, is to use something like the Arduino. Now I also brought with me, I don't have any code for it, but there's another microcontroller board out there that's same mindset as the Arduino, but this is called the Raspberry Pi. But the Raspberry Pi actually doesn't have any analog ports on it. It does have PWM ports, but this particular board is actually a full-blown PC on a card right there. And you can also run robots with this as well, with the Raspberry Pi. That there. But if you look at the Raspberry Pi, you see it's also got an HDMI output. It's got an analog headphone jack. There's a couple of USB ports, 4 USB ports, an Ethernet. There's a Bluetooth, but it's actually the next generation of the ARM processor. It's got 40 pin. This actually you can do industrial strength projects with right there. I'm not going to pass this one around simply because, first off, this is like 180 ring versus that there. Plus, it gets static charges easier. The particular designers opted not to use the Raspberry Pi for several reasons. One is they didn't need to for a simple robot like this. But if you were to do an industrial robot that you were to have a relatively large, complex program running on the robot, not on a PC tied through MATLAB or Visual Studio, then you would need something like the Pi. The Arduino doesn't do much in terms of complex right there. So, again, the servo just basically, this just simply shows that as we vary the pulse width right there, is that they're saying that if we're down to right here, like 1 millisecond for the pulse width, it's going to be at 0 degrees. If we're at about 1.5 milliseconds for the pulse width, it's going to be close to 90 degrees. In about 2 milliseconds, it's going to be 180 degrees right there. So, but that's just simply, that's internal to the design of the servo itself right there. So there are people who design servo motors, but this is pretty much a standard servo design right there. I mean, in other words, industry standard. They're looking at about 20 milliseconds or 500 kilohertz is the normal speed. I think that's right out there. So it's looking for a pulse every 20 milliseconds of a time period between 1 and 2 milliseconds. So we're not using much of its duty cycle right there. And this is one thing that you have to kind of get your head around, is that inside the servo motor itself, there's actually a microcontroller or a small processor that actually controls the motor itself right there. So the servo controller in the Arduino is talking to the actual motor controller in the servo. You know, there isn't a motor that does this. The motor's it's got the electronics built into it in order to know that every 20 milliseconds it's going to get a pulse, and that pulse is going to tell it where to set the motor right there. So, and it's got feedback built into the motor and various other things right there. So, inside the servo, and I'm not going to worry about that. There's a YouTube video. I'll put a link to that there. But right there inside this. And what they're saying is if you take your servo apart, you know, this shows it operating. I wasn't going to do it. That's we'll go ahead and show it right there. But if you take the servo apart, you can see the inner workings. This is actually what this lab, and as I was just saying, there's a microcontroller, a digital circuit inside the servo that actually controls the speed. And you can see the various gears. And the warning is, beware though, if you dismantle your servo, there's a good chance it won't go back together right. So if you take it apart to look at it and see how it works, it may or may not work. As you can see, there's a standard DC motor there, and then the electronics is on the board there on the back right there. So right there. But that's what you would see that there. So with that pretty much covers what I wanted to cover today. Right there. Is just kind of point out there are other types of servos. There's what they call a continuous servo that you can control the speed and the direction by varying the pulse width. Those are a little bit different. That there. I'll talk about those another day simply because I don't like mixing topics in the same day. Right there. I do have an example of one of those that there, and I will probably just do both these labs as a demo, but that there. As I said, if I had 20 servo motors and 20 Arduinos in 20 breadboards, I would just tell you to all go in the lab like you did and just, you know, hook the circuit up, but I don't have that, so I'm going to run it as a demo out there. So, any questions on that there? We're probably looking at a midterm test here before too long, which will probably cover up to the Arduino processor discussion right there. I'll have a review for that probably a week before the test. I've done the test online before. Problem doing it online is I get scolded for that because everybody gets the same grade because you seem to do it as a group. That there, I can't understand that if I put a test online that I give all 30-some people, 40-some people the same questions, I get 40 of the same answers. So everybody gets the same grade, so I have to give it in a classroom setting where I at least vary the grades a little bit between person to person. But I'll go through and I'll tell you exactly what the questions are going to look like, at least a week before that. I'll be putting that together. They'll probably look a lot like part of the midterm or the final exam from last semester, but I'll change some of the questions. But probably, I'm hoping maybe Thursday I might have that put together. So, with that said, I'm going to go ahead and, it's only a 40-minute discussion.